So this is a previous year GATE 1997 question. In a certain double pipe heat exchanger, hot water flows at a rate of 5000 kg per hour and get cooled from 95 degrees Celsius to 65 degrees Celsius. At the same time, 50,000 kg per hour of cooling water at 30 degrees Celsius enters the heat exchanger. The flow conditions are such that overall heat transfer coefficient remain constant at 2270 watt per meter square Kelvin. Determine the heat transfer area required and the effectiveness, assuming two streams are in parallel flow. Okay, and just assume the stream value of Cp is equal to 4.2 kilojoule per kilogram Kelvin. So we have a hot water. It's a double pipe heat exchanger, and we have given the water flow rate of hot water as it's not 50,000 kilogram per hour, and this hot water get cooled from 95 degrees Celsius to 65 degrees Celsius. At the same time, the flow rate of cooling water is also given as 50,000 kilogram per hour. So the flow rate of both hot water and cold water is same, and the inlet temperature of the cooling water is 30 degrees Celsius, but the outlet temperature of cooling water is not given. Also, the heat transfer coefficient is also given as 2270 watt per meter square Kelvin. You have to find the heat transfer area and effectiveness. So divide the mass flow rate by 3600 to convert it into kilogram per second. It is given in kilogram per hour. So divide by 3600. So 50,000 by 3600. So I will get the mass flow rate of the respectively for both hot water and cold water. As both are same, it has the same value as 13.89. Then TH1 is 95 degrees Celsius and TH2 is 65 degrees Celsius. TC1 is 30 degrees Celsius. We don't have the outlet temperature of cold water, only have the inlet temperature. Also U, that overall heat transfer coefficient U is given at 2270 watt per meter square Kelvin. Okay, Cp value they already mentioned. Take the Cp, this water, they already mentioned this water. So we know the Cp value of water. So it will be same for both cold water and hot water. It is 4.2 kilojoule per kilogram Kelvin. Okay, that's spelling mistake. There is not Kelvin mentioned. It is kilojoule per kilogram Kelvin is unit of Cp. In order to find the outlet temperature of the cold water Tc2, apply. We know the heat lost by the cold water is gained by the cold water. So simply apply that heat loss equation, equating. That is, heat lost by the hot water is equal to heat gained by the cold water. Okay, heat lost by the cold water is due to the temperature difference caused. It was initially at 95 degrees Celsius, and due to the heat transfer, it is reduced to 65 degrees Celsius. So that heat loss or heat change due to the change in temperature. Okay, the enthalpy of the change in temperature, how much that heat costs is simply mCp delta T. Okay, so mH into Cph into Th1 minus Th2. Similarly, the gain in heat in cold water is simply due to the uplift of temperature. Okay, Tc2 minus Tc1. So from there I get Tc2 as 60 degrees Celsius. So simply apply the equation of LMTT logarithm mean temperature difference. They already mentioned it's a parallel flow heat exchanger. So for a parallel flow heat exchanger, that LMTD or theta m is simply theta 1 minus theta 2 whole divided by ln theta 1 by theta 2. For a parallel flow heat exchanger, we know theta 1 is Th1 minus Tc1 and theta 2 is Th2 minus Tc2. Okay, you have to know that for a parallel flow heat exchanger, theta 1 is Th minus Tc1 and theta 2 is Th2 minus Tc2. It's a fact. Okay, you have to learn for that for a parallel flow heat exchanger. So simply substitute the equation theta m. I can find theta m as 23.4 degrees Celsius. So I know the equation of that heat transfer equation. Okay, Q is equal to UA theta m. The equation connecting logarithmic mean temperature difference and heat transfer is simply UA theta m. So I already have the Q, right? I already have Q. So I need to find Q. So Q can be defined either by simply taking the heat lost by the hot water or heat gained by the cold water. Both are same value. So here it is taken heat lost by hot water. So you can either take it hot water or cold water. So I get Q. So substituting that value, I will get an area at 32.95 meters square. Okay, you got the answer of the first part. And next part is you have to find the effectiveness. Effectiveness is simply the ratio of actual heat transfer by maximum heat transfer. So actual heat transfer is simply it could be either due to hot or cold. So it can be either MHCP TH1 minus TH2, and that's the actual heat transfer. So the reason why it is actual heat transfer is TH1 minus TH2. Okay, that's what actually, because the temperature difference is actually occurring in the hot water. That what, because the heat lost is gained by the cold water, right? So the loss is occurred in hot water. Simply due to that loss, that's the actual. I mean the change. That is actual is MHCPH TH1 minus TH2, or it could be other due to the cold water difference. Okay, because both are same. That heat loss and heat gain are same. So that actual heat transfer is just you can apply either hot water equation or cold water. But maximum heat transfer is only simply formed due to TH1 minus TC1. Why? Because TH1 is the initial temperature of the hot water, and TC1 is the initial temperature of cold water. That is the maximum possible difference. The maximum possible difference that can occur is simply the difference of TH1 minus TC. The maximum possible heat transfer is simply due to TH1 minus TC1. Okay, because that's the maximum, the difference in temperature that can occur. So both are at the minimum condition, right? So that's the maximum rate or grade at which the temperature can change. So Qmax is simply MHCPH. Okay, you have to apply the hot water into TH1 minus TC1 Qmax. So from that equation you can find effectiveness. Okay, so ratio of actual heat transfer by maximum. So answer will be 0.461. So this is how you solve this problem.